Alright, hi guys. This lecture is going to be the last lecture on our Introduction to Neural Network series, and in this last lecture, we're going to be talking about hyperparameters. So hyperparameters are basically knobs of a neural network that we can basically set before sending it off to train, right? So when a model is training, it's learning its parameters. Those are the weights and biases of our network. But hyperparameters are sort of a level above the parameters, and they control various aspects of the model's behavior, and it's up to the programmer or the developer to choose what are the settings for these hyperparameters, and these are things that we have to choose. And so some of the hyperparameters that I'm going to cover in this lecture, the obvious one being like network structure, how many layers should we have in our network and how many neurons should be in each layer, the learning rate, regularization techniques, batch size, and all the other ones listed. So let's get to it. Okay. In terms of network design, you know, the key thing to remember is that larger networks will usually be able to represent more complicated functions, right? So if you are training a model and you're not able to get past a certain accuracy once you've tried messing with a bunch of the other hyperparameter settings, it may just be that your model is not big enough. So you should just increase your network, the number of layers in your network or the number of neurons in a layer, right? So the key thing to note though is that if you have more parameters to train, that also leads to higher training times because there's just more stuff to compute on every iteration, right? Also, a bigger model is not always better because if you have a bigger model, it may be prone to overfitting. Like, let's say you have some super complicated model and you're just trying to classify digits, which is a relatively simple problem compared to some of the other stuff that neural networks tackle. If that's the case, then it may be that your model will overfit to your training data set, which means like it basically memorizes the patterns that it sees in the training data set, and it's not able to sort of generalize the knowledge that it gets from the training data set and apply it to other distributions of the same data. So that's not good. It's sort of represented by this picture on the right here, where a good model would be the black model, right? Where it successfully separates most of the black and red, but it doesn't get some of them because these look like random perturbations. Like it's sort of random here, right? This red dot should probably is a result of some weird occurrence in the world that this data was taken from. But a model that does like exactly fit this data is this green one, and this is this has overfit to the data. So you want to basically experiment with network structure and try different settings for the number of layers, and make sure you don't overfit. And the way to determine if you overfit or not is usually when you're training these models, you'll have a training data set and a validation data set. So you'll train on your training data set, and obviously, even if you have a super huge network, that would just increase the accuracy on the training data set. But if you ever see that the validation data set decreases the accuracy on that, which you would calculate once you already have a trained model, you would just run the same model on the validation data set, which is separate from the training data set. And then you see that accuracy. If you overfit, then the accuracy on the validation data set will actually be like significantly lower, and it'll drop compared to the training data set. So when the validation data set accuracy decreases, that's when you overfit. So you just want to experiment with different structures. There's no like hard and fast rule. It really depends on the problem. Okay, the next thing that we're going to talk about that also is used to prevent overfitting is called regularization. And basically what regularization is whatever we have for our loss function, um, instead of just having the error as our loss, we also add this regularization term, where this is some constant, lambda, and then we just sum the magnitude of all the weights of our network. for L1, and then for L2 we do that squared. And what this basically does is it punishes large weights, which usually we don't want in our networks. It's if we have smaller weights, that generally means that our network is more stable and not like there's no highly dependable nodes. I'll talk more about that in the future, but basically this punishes large weights, and it also serves as a sort of random noise to our network, because before our loss was solely dependent on this error, but by adding this other term, we sort of inject noise that is not directly related to our performance on the task, and just having this random noise in our loss function uh, basically incentivizes the model to learn a more generalized function, so we don't overfit. Another technique to prevent overfitting is called dropout, and this is a really cool sort of. It's super simple, but it's really cool that it works. And basically, what dropout is that um, you just do everything the same, except during backpropagation, you randomly cut off or ignore some percentage of the nodes. So you don't do backpropagation on some percentage of the nodes. And what this ends up doing is it decreases the number of highly dependable nodes on our network. Because our network, if we're randomly ignoring nodes during backpropagation, it's incentivized to basically, um, it decreases the number of highly dependent nodes in our network. Because if we depend on one node heavily and that node gets cut off, then we basically don't perform well, right? So the neural network basically during backpropagation, it's able to sort of spread out its knowledge across all of its neurons. So there's no like um, one neuron that does something very crucial. I mean, that's not necessarily true, but basically, the fact that it's more spread out, the knowledge is more spread out, allows for greater stability of our network. Okay, and this is going to be a review of some concepts that we covered in the last lecture, but just briefly. Um, Up till now, most of the examples that we've talked about involve stochastic gradient descent, where after every single training example, we perform an update to our weights and biases. But it turns out that that's not actually always the best method for optimizing our weights and biases. There's two other main techniques. Those are called batch gradient descent and mini batch gradient descent. So in batch gradient descent, um, what we do is we look at every single example in our training data set, and then we compile the aggregate of all of the updates that we would have made, and then perform one large update at the end after seeing every single example. So we store all of like the updates that we would have made, and at the end we average all of them together. The problem with this is like data sets can be very large, and if your network is also large, it's it you can soon run out of memory on your computer, to hold all the data regarding the updates. So you can't really do that in most cases. So a sort of hybrid solution between updating all at once at the end of all of your training dataset examples versus every single example is mini batch gradient descent, which is the second thing listed here. And in mini batch gradient descent, you look at maybe 8 images and then you perform an update, and then the next 8 images, and then you perform an update, and so on, right? So it's a sort of hybrid solution between looking at every single example in your data set, and then uh, it's a hybrid between updating after every single example in your data set versus batch gradient descent, which is like updating after you've seen every single uh, example. And so this is usually what is mostly used in practice. And basically, the hyperparameter in this scenario would be the batch size. So how many images do you want to make an update after? And usually these are because of like memory. Um, Basically, it's stuff related to computer architecture. You want to have batch sizes of multiples of 8, and usually you just choose the largest batch size that the memory on whatever computer or server you're training on allows for, right? Um, so the reason why this is memory, like RAM, is because all of these are getting stored during the execution of the program, and then they get implemented at the end of the backpropagation step. So that's why it's dependent upon RAM. Um, and so that's just a hyperparameter that you can set. Usually, you just want to set the highest batch size. And this graph basically represents, you know, what these different optimization techniques involve. The purple thing here is called stochastic gradient descent, and you see that the path that it takes towards this convergence point here. This is a contour plot, so this line represents like a high value, and then this line represents a slightly lower value, and then this line represents an even lower value, and so on. So this purple line, which represents stochastic gradient descent, is taking a really like windy path towards the minimum. And that's sort of because every single example moves in some certain way, and that doesn't always mean that it's moving in the correct way with respect to every single example in your training data set, right? Like it's not the optimal path, it's just the optimal path for that specific example. So that that's sort of alleviated when you have mini batch gradient descent. Even though it's still kind of jagged, you're moving in a smoother fashion towards this convergence point. And batch gradient descent is even more smoother, because you're averaging the results of the whole data set, um, the updates that you would have performed from the whole data set, and then you're moving. So this is even better. Okay. Next, something that we also covered in the previous lecture was learning rate. And learning rate is basically this term that we multiply our gradients with when we're updating the weights and biases. So the reason why we have this learning rate, as mentioned before, is that let's say we were here on our loss function. This is a simplified loss function where there's only like one parameter, um, like one independent like parameter, and then the loss is another axis. So it's a simplified version, but let's say that we start off here and we compute the gradient, and then the negative of the gradient tells us to move in this direction, right? Because that's how we minimize the function. So in order to move this direction, we have to move our parameter, uh, our weight or bias this direction, right? So obviously that it would be nice if we moved here, but let's say we took such a big jump of this parameter that we ended up over here. Now, actually, that's sort of worse than the loss that we had over here, right? Because we moved up the graph. Even though we moved our parameter in the correct direction, we moved it too much. And then if we do that again, you can imagine we end up all the way over here, because when you take the negative of the gradient here, that tells you to move the parameter in this direction. But if you move too far left, then you'll end up even worse, right? So a learning rate, which is usually a small number, like between 0 and 1, that basically minimizes. It decreases the magnitude of the steps that you're taking when you're performing gradient descent, so you don't end up making these bad mistakes, right? Even though like you always move slowly towards the convergence point. So a very low learning rate will lead to um, very slow learning, and then a big a large learning rate may actually lead to no learning at all because you keep getting worse. So the key thing is to just find like a value that's in between, that's just right. Okay. Okay, this was not covered in the previous backpropagation lecture, but something this is very important. It's called the vanishing gradient problem. And basically, let's say that we have 4 layers in our network. And in the fourth layer of our network, we all the neurons are pretty much optimal. Like they're the values that they are acquiring are either very close to 1 or very close to 0. Like they've basically learned everything that they could have learned, right? So in backpropagation, the resulting delta term that we compute as such, this would be since we're looking at the weights and biases of the last layer, we would use this delta formula. Um, we would compute this delta formula. And since we've already learned most of these things, and they're pretty optimal, their values are pretty optimal, this sigma, the derivative of the sigma term, would be close to zero. And the reason for that is because if we are optimal, then whatever values go into the sigma function here, the sigmoid function, they would either be on this part of the graph or this part of the graph. Because, we'd want to, if we had learned everything properly, then the values would be high or low, depending on our exact problem statement. But, if it's here, that sort of means that we haven't learned everything yet. But if we have learned stuff, then we would end up over here or over here. Okay? And assuming that that's true, then the derivative at this point of the graph or this point of the graph is close to zero, right? It's not going to be exactly zero, but it gets very close to zero. And this red line is the derivative of the sigmoid function. And so noticing that, the delta terms of that layer would be close to zero. The delta matrix for that layer would be close to zero. And then once we back propagate even further, note that all the previous delta layers, the delta matrices, actually depend on the delta matrix that we just computed. So if this delta matrix that we just computed was close to zero, like if its values were all like near zero, then that would have like an effect on all of the other delta values in the previous layers. And what ends up happening is that as you go further and further into the network, all of the gradients kind of get like diluted, like they become all closer to zero, even if some other neurons in our network haven't learned as much as they needed to. So this is called the vanishing gradient problem, because as you go further back into your network, the gradients sort of vanish, like they tend closer to zero. And so we need a way to fix this. So the key thing to note is some ways to fix this are by using activation functions, different activation functions than the sigmoid function. So here, this graph basically shows three different activation functions. The red is, I'll start with the green first. So the green is basically called a tanh function. It's the hyperbolic tangent function. And the key difference between the sigmoid function and the tangent function, tanh function, is that the tanh function's output values are from -1 to 1, whereas the sigmoids are from 0 to 1. And we're not going to discuss like the proof of why exactly this makes a significant difference, but basically the fact that you're not multiplying by 0 in some instances, and instead you're multiplying by -1, that actually sort of solves the vanishing gradient problem. Another activation function that is widely used is the ReLU function. And another advantage of the ReLU function, other than the fact that it also solves the vanishing gradient problem, is that it's very simple to compute, right? It's just either 0 if our input value is negative, or it's just the line y equals x for any positive input values. And the derivative is also very simple to compute. It's either 1 or 0, right? So that, in addition to being being very fast for computations, the ReLU function also solves the vanishing gradient problem because the derivatives are always constant. That basically solves the issue that we stated on the previous slide. And lastly, some additional choices that you can make as a programmer are making these sort of modifications to the backpropagation algorithm. So one modification is called momentum, where you sort of, it's sort of like the same idea as momentum from physics, where each step size, each step that you make during backpropagation depends on the size of the step that you made previously. So if you've been making large steps, then try to also make a large step this time. But if you have if you've made a small step on the previous stride, then make a smaller step on this side, right? So basically what that means is if if you still haven't converged yet, keep going like faster and faster. But once you see that you're okay, I'm about to converge, then sort of slow down a little bit. Some other things to note are decay, which is basically just multiplying all the weights of your network by a constant that's less than one. And what this does is it prevents exploding values. So you don't want super high values in your network because, as we mentioned before in the beginning of this lecture, having super high values kind of leads to a more unstable network. And so by doing decay, what you can do is prevent these exploding values. Another thing is like epsilon, which is on every backpropagation step, you just add random noise to the weight values. And what this does is it decreases the probability that you overfit. Because if you're randomly adjusting these weight values, the network can't depend on that, sort of forces the network to learn a more generalized function. And there's many more that I haven't listed, but the key thing to note here is that if you ever like implement these networks using any of the deep learning frameworks like TensorFlow or Keras or PyTorch, all of these are just like parameters that you can give into these functions, and they'll take care of it for you. And the documentations on all of these libraries are pretty extensive, and they explain what each of these things does in a bit more detail. So I encourage you to check those out. And a final and very important choice that you can make as a programmer is what sort of optimizer you use to train your neural network. Right, so we've previously discussed all these different variants of gradient descent: stochastic, mini batch, and batch gradient descent. And this is just sort of the run of the mill um, gradient descent algorithm that also requires the least amount of computation compared to the other two techniques that I'm going to talk about. So the first other technique is called RMS prop, and what this does is it um, changes the learning rate according to the magnitude of the gradients that were calculated in the past few you know iterations. And this is specifically useful in RNNs. And basically, this allows for a more efficient training process. Um, there's another thing called Atom, which also modifies, like, during training, it modifies the learning rate. So we don't just have like one alpha value, it'll keep changing during training. And in addition to what RMS prop allows, Atom also has the sort of momentum functionality built in. So if you have been taking large steps, then continue to take large steps. But if you sort of tended towards smaller steps, then get smaller, right? And usually, Atom is in a lot of scenarios, Atom is the one that you choose. It's just like the straightforward. It's sort of easier. And more efficient than gradient descent or RMS prop. But note that in recurrent neural networks, which we're going to be talking about in the future, RMS prop is pretty helpful. Right, and that's it. Thank you for watching.